Suppose you want to remove a nucleon from the nucleus, so like either a proton or a neutron. So work is going to be required because you're going to have to overcome that strong nuclear force that binds everything in the nucleus together. Now, this binding energy of the nucleus, or this EB, it's basically the energy that's required to separate all the protons and neutrons in a nucleus and to move them infinitely far away. So it's basically how much energy you have to put in to entirely disassemble the nucleus. So the binding energy is going to be the difference between the energy of the nucleons minus the energy of the nucleus. So the energy of the nucleons is sort of the energy of all of the parts that are separated, versus the energy of the nucleus is the energy of all the nucleons together. So basically, another way we like to think about the binding energy is the potential energy that's stored inside the nucleus. Now, in 1905, Albert Einstein proposed the mass-energy equivalence. So this is the equation that probably every single person knows from childhood. They might not know what it means, but they've certainly seen it. They see this E equals mc squared. We have this little delta m. We're going to explain that. So this relates the idea of energy and mass. So E is going to be that energy in joules. This delta m is going to be this thing called the mass defect. We're going to talk about that a little bit in kilograms. And then c is our speed of light. So in a nuclear reaction, we're looking at the conversion between mass and energy. So the law of conservation of energy still is going to apply in a nuclear reaction. So what we'd like to look at is we'd like to see how that energy and mass relate to each other. So we're going to look at a carbon-12 atom to kind of highlight this. So if we have carbon-12, its mass is defined as being exactly 12 U. That is how we get the because we know that the atomic mass unit is defined as exactly 1/12 of a carbon-12 atom. So a carbon-12 atom is going to have a mass of 12 U. So a carbon-12 atom is going to be made up of 6 protons, 6 neutrons, and 6 electrons. So we can add all the masses of the constituent pieces of the carbon-12 atom, and we're going to find that separated, they all have a mass of about 12.09894. This number is not the same as this number. So the total mass of all the parts of a carbon-12 atom separated, it's slightly more than the mass of all of the parts together. So when we join all those pieces together, we have a reduction in mass of about 0.09894 U. That deficit mass, or that difference, this difference is what's going to be converted into energy. So that energy is what we will use for whatever application we need it to. So that's kind of what's going on. It looks like there's mass missing. It's not missing. We still have to account for it. That mass has just been converted into energy through E equals mc squared. So this mass defect, we will take the mass of our nucleons and we'll subtract off the mass of the nucleus. So the nucleons being everything separated, the mass of the nucleus being when everything's combined together. So let's look at the mass defect and the binding energy for sodium-23. So sodium-23, it has an atomic mass of 22.989769 U. So we'd like to find the mass defect and the binding energy for this. Alright, so the mass of the nucleons, it's going to be the mass of the protons plus the mass of the neutrons. Now, in this nucleus, we have an A value of 23, we have a Z value of 11, which is my number of protons. So I know I have 11 protons in this nucleus, and that means my number of neutrons, which is going to be my atomic, because the 23 represents the number of protons plus neutrons, and I know I have 11 protons. So this tells me we have 12 neutrons. So and I'm going to put a little sum symbol because we want the total mass of protons plus the total mass of neutrons. So in this sodium-23 nucleus, it's made up of 11 protons, so we need 11 protons plus 12 neutrons. So we want to find the mass of all the parts of that sodium-23 atom. So we're told the mass of the proton is about 1.007276 U, and then for the neutron, it's 1.008665 U. So that's the hard part with a lot of these questions, is we have a lot of decimal places, so a lot of places to make mistakes. So be really careful when you're entering numbers in the calculator. So with that, we're going to get about 23.184016. So that's the mass of all the pieces separated. Now, if we combine them together, the sodium-23 atom is going to have a mass of 22.989769. So that mass defect is going to be this difference between the two. So we're going to take that mass of everything separated minus that mass of everything combined together. So we are going to have, again, lots of numbers to put in here. So we're going to have about 0.194247 U. So what this mass represents is this is how much the mass decreases when we join everything together. Now, that mass didn't go away. What's going to happen is this mass, or this mass defect, this is going to be converted to energy. So this is converted to energy. We'd like to find out how much that is. So we are going to use this E equals mc squared. Now, for E equals mc squared, the mass defect has to be in kilograms. So this has to be converted to kilograms. So we know that 1 U is 10 to the minus 27 kilograms. That is on the data sheet. So our mass defect in kilograms is going to be about 3.22450 times 10 to the minus 28 kilograms. So this is the number that we're going to use to calculate the energy. So we know that E is equal to the mass defect times c squared. So again, this must be in kilograms. So the mass defect is that 3.22450 times 10 to the minus 28 kilograms, and then we have our speed of light squared. So if we calculate all that, the energy we are going to get for this, so we're going to get about 2 points. So we want 6 significant digits because that's what we get from our mass defect. So these digits after the 0 decimal are the significant digits. So we're going to get about 2.90205 times 10 to the minus 11 joules. So based on that deficit in energy, that deficit in mass, this is the energy we're getting. Now you might say, that's pretty small. You're correct, it is. But you got to think of the scale we're working on. We're working on a subatomic scale. And keep in mind, when we're having like a nuclear reaction, there's billions upon billions upon billions of particles. So this is just for one reaction here. This is just for one atom. So keep in mind, we're going to have lots. Now, with that binding energy, sometimes we're going to refer to this thing as binding energy per nucleon. So the binding energy per nucleon tends to deal with the stability of an atom. The higher the binding energy per nucleon, the more stable the atom is going to be. So we have this very well-known chart in nuclear physics. This shows the binding energy per nucleon as a function of atomic mass number. So we kind of see like it spikes up and then starts to go down. So based on this chart, we would say that our most stable nucleus is iron 56. This graph we're going to look at a little bit more later because we're going to have to discuss fission and fusion, but we'll get to that later. So last thing is, let's look at an oxygen-16 nucleus. We're told that the mass of the nucleus is 15.9949 U. We know the mass of a proton is 1.0073 U, and that of a neutron is 1.0087 U. We'd like to determine the binding energy per nucleon in an oxygen nucleus. So oxygen-16, this is the A value. So to write this in the form like the AZX, well, we have the atomic mass number of 16. On the periodic table, oxygen is element 8. And then we can write it as such. So that is how we write this in nuclear notation. So we know A is 16. We know Z is 8. We know the atomic mass number is the number of protons plus neutrons. Well, if I have 8 protons, that means I'm also going to have 8 neutrons. This is going to allow me to determine the mass defect because I want to find the mass of the nucleons first. So the mass of the nucleons is going to be the 8 mass of the protons plus 8 mass of the neutrons. So let's calculate that. So that 8 times the mass of the proton plus 8 times the mass of the neutron. So let's see what we got going on here. So we got 8 times this 1.0073 plus 8 times 1.0087. So we're going to get about 16.128 U. So or 16.1280 U. So that is the mass of all our nucleons separated. So the mass defect, we're going to take that mass of everything separated and subtract off the mass when everything is combined, that 15.9949 U. So that is going to give us our reduction in mass that gets converted into energy. So we're going to have this 0.1131 U. So that mass defect, this gets converted to energy. To find the energy, we would certainly like to have this in kilograms, because E equals mc squared only works when this is in kilograms. So we're going to multiply this by 1.66 times 10 to the minus 27 kilogram per atomic mass unit. So this mass is going to be about 2.209 times 10 to the minus 28 kilograms. So that's the reduction in mass that we've had. That mass is going to be converted into energy. So we have our E equals mc squared. So we have that 2.209 times 10 to the minus 28 kilos, 3.00 times 10 to the 8 meters per second squared. Don't forget our squared there. So this is going to give me the energy in this reaction. So I'm going to get about 1.989 times 10 to the minus 11 joules. But we didn't ask for energy released. We asked for binding energy per nucleon, or energy per nucleon. So we have the energy. We know that there are 16 nucleons. So the last step in this is the binding energy per nucleon, or EB over A. We're just going to take that 1.989 times 10 to the minus 11 joules, and we're going to divide it by 16 total nucleons. So what that's going to give us is that is going to give us a value of about 1.243 times 10 to the minus 12 joules per nucleon. So that is our energy. You'll notice in the chart it has the things in mega electron volts. Very common in atomic physics. We don't usually use joules a lot for energy. We usually use electron volts or some variant of that. But just be aware that if we're asking for energy per nucleon, don't forget to divide by the total number of nucleons at the end here. So in this case, in oxygen, we have 16 nucleons.